Good afternoon, class. Today what I'd like to do is to start a series of videos on chemical bonds. So in this introduction video, what I wanted to do was go over the types and number of chemical bonds that are typically seen in nature. So first off, we need to define what a chemical bond is. So a chemical bond occurs when the valence electrons of different elements pair together or combine in order to fulfill the octet rule. This can be done either ionically or covalently. So what does that even look like? And what do I mean by types and number of bonds? So in nature, what you will find are single bonds, double bonds, and triple bonds. Rarely do you find a quadruple bond, and those are usually under very specific circumstances, so I've left them out of this video. And just to make sure that we're not stepping into chemical reaction territory, because that is a future video. I wanted to do this video with chemical bonds when elements pair with the exact same element. Okay, so here we go. What are some of these examples so today's video is going to be mostly on the number of bonds and how they occur and why they occur using the Lewis dot structure, which we did in a previous video. Next time I'll go over ionic bonds and then, of course, covalent bonds. And I'll show you different ways that elements combine with each other in order to make certain structures and also certain other molecules in order to fulfill the octet rule. So we'll start with the single bond. And the best example of that is hydrogen. In nature, you will almost never find a single hydrogen atom just floating around somewhere. It will almost always get paired up with something. And in the case of hydrogen gas, that means that hydrogen will pair with itself. So we've got a lone hydrogen atom here and a lone hydrogen atom here. Now, what I did was to show the difference between the valence electrons. I denoted one of them with a dot and the other one with an X. So what happens is when you combine these two hydrogens together, that's what this notation means, the two hydrogens sharing each of their valence electrons. Now, that may not look complete because a completed valence set should have 8. However, because this is hydrogen, the next noble gas closest to it is helium, which has a total number of valence electrons of 2. So, in this case, this would actually be complete for hydrogen. So hydrogen would be very happy in this configuration. Now, most of you and chemists from all centuries included, don't like this. I mean, most of you probably will not like this kind of notation and will not want to write this kind of notation at all, as much as possible, pretty much. And chemists throughout the centuries have wanted to avoid that as well. So what they did was they devised this called bond notation, where they would draw a line like so, and this line right here denotes a chemical bond. The number of lines is the number of bonds. So in this case, we've got a single bond here and a single line here, which means that is a single bond between two hydrogen atoms. Let us now move on to a double bond. And the best example of a double bond that is found in nature is oxygen, molecular oxygen, or O2. So what we have is we've got, from our Lewis dot structure, we have oxygen 1, 2, 3, 4, 5, 6, right? We're going right around just following the Lewis dot structure rules that we established in the previous video. Also, from the rules from this video, this oxygen has valence electrons as dots, and this oxygen has valence electrons denoted as X's. So what happens is that what that leads to is that you've got these different these oxygen valence electrons are already paired up. This is known as a lone pair. These lone pairs are very stable. It's when you have unpaired electrons that chemical bonds occur, because those unpaired electrons don't like to be alone. So what they do is they start to share So one of the unpaired electrons drifts over to this oxygen atom. One of their unpaired electrons drifts over to the other one, and so you've got two sets of um, pairs of oxygen valence electrons combining with each other. And now, if the oxygen atoms stay close enough, what you find is that they become they become close, and also they now have an equal, and they both now fulfill the octet rule, and will combined, each one has now 8. They fulfill their valence electrons in the octet rule. However, as you probably noticed with hydrogen, nobody wants to write this, and it gets really messy right over here. So this notation, while it is instructive, it's not very practical for when it comes to writing out chemical bonds, chemical reactions, molecules themselves. So what you will notice chemists do is they will take this, and like they did here with this single line as a bond length, they would say this, there's 2 of them, so that's 2 lines. Do they write the lone pairs? No, they ignore the lone pairs, but just so that they can, because the bond length is actually more important. The chemical bonds are more important to the overall structure of the molecule than anything else. The lone pairs are important, but they can be relatively ignored when it comes to the final drawing, because it doesn't really affect anything. It is something you need to keep in mind because it does affect the physical structure of the molecules that form, but in general they can be safely ignored when it comes to writing it out, because those lone pairs don't mix with other lone pairs, so they kind of push each other away. So this would be a double bond. Now, you may have noticed that I drew something else over here, and you might be wondering what that is. The reason I did this was because this doesn't look very convincing when it comes to what a bond should look like. This is more in the vein of the Lewis dot structures that I was trying to draw it out here. But if you really want to see what it would look like to make it look a little bit more like, kind of like how you would physically combine those orbitals and those valence electrons, it would be more like, instead of them being the lone pairs being at right angles to each other, because remember, electrons repel electrons, they push each other away. So they would actually take up an orientation more like this, where they would be at an angle, maybe like at a 45-degree angle over here and over here. Same thing over here and over here as well. So that's a double bond. Now we're going to move on to the triple bond. This is something that we call pretty much the strongest bond naturally occurring in nature, okay? Because there's 3 of them. And as you noticed, over here, these hydrogen atoms don't really have to get that close for me to draw out the valence electrons coming together. I have to draw them, if I were to really draw them out, like in this case, they notice those oxygen atoms are much closer together than the hydrogen atoms are. Nitrogen bonds, nitrogen atoms with their triple bond actually come out even closer together, which is why triple bonds are actually really, really hard bonds to break. So, with a triple bond, it usually occurs in the nitrogen atom or anything in the nitrogen group. So, phosphorus, arsenic, antimony, and bismuth. What happens is you've got 3 unpaired electrons here. So when nitrogen combines with nitrogen, each of those unpaired electrons connects with each other. So we've got like our dots here, dot with an X, dot with an X, dot with an X. So all those valence electrons are coming together. Notice that they're even more strongly attracted to each other. So now you've got 3 lines, 1, 2, 3. So that is what a triple bond looks like. And again, I didn't write in the lone pairs over here because generally the tradition is chemists will ignore those, because the bonds are actually where everything occurs, because it's actually a whole lot more important. In fact, bonds, because of their length and their and how strong they are, they can actually store quite a bit of energy, which is why they basically say that nitrogen bonds, in order to break, or at least triple bonds like this, in order to break them, you need something akin to lightning in order to break this triple bond because you need enough energy to convince all those bonds to get rid of each other. And that only occurs usually in a lightning strike, which is why nitrogen is actually a really stable compound. And in fact, it's about 70% of the air that we breathe, and we don't even notice it. Doesn't even affect us because it's very inert, and it very much stays like this, and it's perfectly fine in this regard. It takes quite a lot to get nitrogen to actually combine with other elements, which is also why the nitrogen cycle, like you may have learned either in biology or in previous science classes, would have been very key to life on Earth, because nitrogen does not naturally bond with other things unless there is more energy than it would take to bring those nitrogens together. Same thing with oxygen, but because the double bond is so much weaker, it allows the oxygen atoms to stay there, and even allows them to bond even though they have a double bond here. Those double bonds are more easily broken, and oxygen actually is more easily bonded in a covalent sense more than anything else. So that is an introduction to chemical bonds. Next time I'll be going over ionic bonds and then covalent bonds. Good luck in your studies, and may the force be with you.